So yeah, hello, I'm Jimmy. Good afternoon, everyone. I'm Nandini. So today I'll be doing the first problem solving session of your NPTEL course, Introduction to Atmospheric and Space Sciences. So this is our first class. So I think I'll start with a short introduction of myself. So yeah, as I said, I'm Nandini. I'm currently doing PhD in the School of Earth, Ocean and Climate Sciences at IIT Bhubaneswar. Basically, I'm from Kerala. I have done my master's in MSc Meteorology from Cochin University of Science and Technology, and I have a bachelor's degree in physics. Okay, so yeah, that's about me. I think since this is our first class, maybe I would also like to know like what are your background. Whoever have joined, I also would like to know like what you're working on or what you're doing and all those things. So if you can introduce yourself, it will be great. You can type in the chat box also. I hope whatever I'm telling, my audio is clear and my screen is visible. Please do confirm that. Yeah, so anyone would like to start? Okay, so yeah. Hi Nikita, you're doing your master's in physics and you are also from Kerala. Nice. Which university actually, Nikita? From where you're doing your master's? Okay, and next we have Sujay. Okay, Providence College, Calicut. Okay, so then we have Sujay. Sujay is in his first year in bachelor's in electronics at Hindu College, Delhi University. Okay, nice. Ishika, right? Ishika is pursuing her master's in physics with specialization in material science and nanotechnology. So we have like variety of 2 masters in physics, 1 bachelor of electronics. Then others. You can unmute yourself and speak also if you would like to. Yeah, it's fine. I was just telling whoever want to can like unmute and speak, or if you're fine with just typing, that is also fine. Okay, so we have a master student from atmospheric science background also, Deepika. Hi, Deepika. You're from Fakir Mohan University. You're first year or you have just done first year, right? Okay. Which year, Deepika? First year. Okay. So you will be familiar with all these things, maybe whatever is there, the contents of the course. You're already familiar with these things or things? Okay. Then we have Tejashwini. She is also doing masters in physics from Shastra University. Hi, Pankaj. Pankaj, you would like to speak? I have been to Shastra University once. I just would like to say that during my masters, I initially got admission there. Then I shifted to KISAI. So I have been there to the university. Okay, so Pankaj is from uh, Pankaj is also doing masters in physics and from Vikram University, Ujjain. Okay, nice. So I think most of the people are doing masters in physics. Anyone else? Yes, Abhiram, Central University of Karnataka, again masters in physics. Okay. So people who are doing masters in physics, like why you'd like to know more about atmospheric and space? That is the reason you have opted the course, or do you have this course as a part of your curriculum? You found this study interesting or this region interesting, that's why you have taken this course, or do you have it as part of your curriculum? Okay, again we have two more masters and physics students. One is Sadhana, she is from Shivaji University, Kolhapur. And Muthu Ganesh, he is doing his masters in physics again from Tamil Nadu. Manon Maniam, Santaranar University, if I'm right. Then, yeah, from same university we have another one, Ramalakshmi S, masters in physics. Okay, nice, nice. So how do you find this course interesting after I think 2 weeks classes have been uploaded in the site, I guess. So how do you find the course? Is this interesting? How do you feel about it? Anyone would like to share? Okay, and Sakshi, we have. Okay, thanks, Nikita. So you found it interesting. Okay. Oh, okay. Tejashwini is doing a project related to this. Okay, nice. Uh, what exactly you are doing? Can you elaborate it a bit? So I'm basically working on urban. As I told you, I'm doing my PhD here at IIT Bhubaneswar. So hope I'll complete it soon. This is my fifth year. So I'm basically working in urban climate. So I'm trying to analyze the temperature and rainfall changes over Bhubaneswar city using a regional climate model. So I'm yeah. So how as the city is expanding, how the temperature and rainfall changes are changing. Those things I'm trying to look into. Okay. So yeah, Sakshi. Okay, physics-based ionospheric model. Okay, nice. Thank you for telling. Yeah, we have Sakshi. She is also from. She's from Shivaji University, Kolhapur. She's also doing her masters in physics. Okay, okay, nice. If anyone would like to introduce, you can do so. We will slowly start the class. Okay, Pankaj, you have the topic as part of your syllabus. Okay, nice. Okay, then we'll get to know as the as it progresses also. I think we will just begin. So yeah, so today is the first problem solving session of the course Introduction to Atmospheric and Space Sciences. So today I will it will be kind of a revision to what all things that you have learned in the course during the last 2 weeks, and then we will do one or two problems also. So I'll begin with the Sun Earth system. So as we all know, basically Sun is a star which is capable of producing its own energy and light, and Earth is basically a planet which is one among the various other planets in the solar system, for which Sun is the primary source of energy. So this is the Sun, and here we have the Earth. So all the physical, chemical, dynamical processes in the atmosphere of the Earth is basically driven by the energy that is being emitted from the Sun. sun is the primary source of energy. For Earth, and all the physical, chemical, dynamical processes in the Earth's atmosphere is basically driven by uh, the energy that is emitted from the sun. So Earth receives energy from the sun in three different forms, which is basically in the form of electromagnetic radiation, then in the form of particles, just basically through solar wind. Then it also receives energy in the form of magnetic. Or these are the three different ways in which the Earth and the sun interact with each other. So it receives in three different forms. Basically, the electromagnetic in the form of electromagnetic radiation, and in the form of particle, which is basically the solar wind, and then in the form of magnetic field. Among this, electromagnetic radiation is the most important one, or through that the Earth receives maximum amount of energy from the sun. Now let us look at the more details about the sun. So as I said, sun is basically a star, and this is the only star in the solar system, in our solar system. And when we compare sun with other stars in terms of its mass, it is basically medium mass dwarf. Compared to the other stars, it is basically classified as a medium dwarfs, where we have different stars ranging from super giants to dwarfs. So among the other stars, sun is basically a medium mass dwarf, and based on its brightness, it is basically a medium bright dwarf. Where we have very bright supergiants and very dim dwarfs, sun is basically a medium bright dwarf. And if we look at the temperature or color compared to the other stars, sun is basically having yellow color. Now when we look at the color, sun is basically having yellow. There we have stars with have colors ranging from very hot blue to cool red. Okay, so these are some important aspects about the sun. And then when other important, what do you say, terms or parameters related to sun. So sun is basically it is just one it is a normal star among more than 100 billion stars in our galaxy, and the diameter of the sun is basically 390 kilometer, which is basically 110 kilometer times of the Earth, the diameter of the Earth, and the mass is 1.2 into 10 raised to 30 kilogram, which is 3,33,000 times the mass of the Earth. And when we compare the mass of the Sun with the entire mass of the solar system, almost 99.8% of the mass of the solar system lies in the Sun. So, like the other planets, along with the Earth, constitute very negligible mass of the solar system. Almost the entire mass of the solar system is concentrated in the Sun itself. Atul Krishna is asking, how was the color determined even though sun looks white uh, from space? I think based on the temperature, they are so generally when we say we generally what do you say, heat an iron rod or something, then it is at its highest temperature it appears around like it will be like very bright blue will be there. Then as the temperature decreases it comes from very bright blue then to red then to yellow, then it kind of decreases like that. So when we look at the when we compare it with the temperature of the other stars, it appears to be yellow. Like from very hot, it basically ranges from very hot blue to very hot blue to cool red. So in that range, they are telling like it appears to be yellow. So very high temperature means it appears to be what we say blue in color. Then as the temperature reduces, the color kinds of dims blue, red, then orange, yellow, kind of like that. So in that scale, they are telling it is yellow in color, appears to be yellow in color. So how did they determine the color? Like with respect to what? Or like in like it's like based on the appearance with respect to what, or as are they determining from the earth or from somewhere else? That I'm not sure. I will also have to look at it. So I think based on the temperature, like with the highest temperature appearing to be blue, then as the temperature is decreasing, the color is kind of reducing from blue to red to orange, yellow like that. In that scale, they are telling it as yellow. So from with respect to which space or from where they are looking, or from which space it is appearing to be yellow, that I'm not sure. I will have to check it. I will check that and I will let you know. Is that fine? So I will check it and I will let you know. So yeah, so we were talking about the mass of the sun. So mass is basically 1.2 into 10 raised to 30 kilogram. As I said, most of the mass of the solar system entirely lies in the sun. 99.8. Almost all masses lying in the solar system. The remaining planets along with the Earth is basically very having very less mass. Is contributing very less mass to the entire mass of the solar system. And now when we look at the temperature of the sun, at the surface, the temperature is around 5800 Kelvin, and at the core, it is around 15.6 into 10 raised to 6 Kelvin. So it is very hot at the surface, sorry, very hot at the core, and as we come to the surface, the temperature is reduced. So that's the temperature. Then when we look at the composition of the sun, 92.1% of the sun is comprised of hydrogen, 7.8% is comprised of helium, and the remaining 0.2% is comprised of other naturally occurring elements. So that is the basic composition of the sun. So most of the sun is comprised of hydrogen. Then the second dominant constituent is helium, and then the other naturally occurring elements constitute around 0.2%. Now, when we look at the luminosity or the brightness of the sun, it is basically having a value of 4 into 10 raised to 26 watts. That's the luminosity of the sun. And as we know that the Earth is rotating on its own axis. And how do you define a day? How much time the Earth will take to complete one rotation? You know, so yeah. Can someone tell me how much time the Earth will take to complete one rotation along its axis? 24 hours. So it basically takes 24 hours or 1 day to complete one rotation along its axis. Now, when we similar to Earth, Sun also rotates along. It also rotates on its own axis. And when we compare the time the Sun takes to complete one rotation, so when we look, it basically takes 24.9 Earth days. So Earth takes 1 day to complete one rotation. So compared to the time that Earth takes, it takes basically 24.9 times greater compared to that of the time the Earth takes. And as we can see, interestingly, there are two values. So they are telling like it takes 24.9 Earth days in the equator and it takes 29.8 Earth days in the poles. So basically the values are different at the equator and poles. This is because the sun, the rotation of the sun is not uniform across its latitude. So in case of Earth, the Earth as a whole rotates, then we get 24 hours to complete one rotation. But in case of the sun has a different speed of rotation at different latitudes. It doesn't rotate as a whole. It rotates at different speeds at different latitudes. So it makes it so complicated. So basically the sun revolves faster at the equator, and as we go up to the poles, it is becoming slower and slower. That's why when we look at in the poles, it is taking more time, whereas in the equator, it is taking less time. So the speed is higher at the equator, whereas it becomes slower as we go to the poles. Because of this difference rotation speeds at different latitudes, it is known as differential rotation. This phenomenon of having different rotational speeds at different latitudes is known as differential rotation. So this is known as differential rotation. So because of this differential rotation, this complicates the magnetic field related to the sun. Okay, so that are some important parameters related to the sun. So basically the diameter of the sun is 1.39 into 10 raised to 6 kilometer. So yeah, Ishika is asking what is the main reason for the difference in temperature of the photosphere and the corona. Corona or core. Corona is basically the atmosphere of the sun. You are asking about corona or core. Corona only you are asking about, I guess. And then Tejaswini is asking the length of equator is greater than poles, but why does it rotate at more speed at equator? Ishika, what is the difference between the why the temperature is different at the core and the surface? We will be discussing like how the energy is transferred from the core and the core to the surface. We will discuss in the coming slides. And to answer Tejaswini's question, the length of equator is greater than poles, but why does it rotate at more speed at equator? It doesn't have anything to do with the length actually. It is not like since the distance is more, it is taking more time. Uh, okay. Can it be because of the bulging of the sun at the equator? Sujay is asking. So why actually this differential rotation is happening is actually not that simple. Like, is it because of uh, like has it is it because of the physical nature of the sun, or is it because of the as like Tejaswini was telling, like is not Tejaswini, Tejaswini was telling, like is it because of the distance, length of the equator is more, length of the poles is less, is because of that it is rotating at a faster speed at the equator. So this is basically an active area of research. So still we are not sure why it is actually having a differential rotation. Uh, it is due to this. It is very complicated, and it has it basically due to the turbulent nature of solar convection. Um, so I think this is still an active area of research which people are working on. So I can't. I'm also not. I can also not tell a straightforward answer like why it is actually having, why it is higher at the equator and why it is lower at the poles. So I think we'll have to look at it. I also can't give a straightforward answer like actually why it is actually. This is actually an area of research. Okay. So yeah. So Ishika was asking about the corona only. Why does temperature difference in corona and sun surface photosphere? So yeah. So as I said, the surface when we the surface of the sun is called the photosphere, which is at the temperature of 5800 Kelvin. And corona is actually a part of the solar atmosphere. So solar atmosphere basically has two layers. The first layer is the chromosphere, and the upper layer is the corona. So the surface of the sun is at a temperature of 5800 Kelvin, whereas the corona of the sun is at a temperature of 3.5 million degree or 2 million degrees Celsius or 1 million Kelvin. It is at a higher temperature. So why it is happening so? That's what the Asian was asking. So so there happens to be very tiny explosions on the sun surface, which may contribute to the higher temperature that is seen over the corona. And like there are different yeah, it is said that it is due to the interaction between the sun's magnetic field and the plasma. Also, as I said, it can be there are very tiny explosions that are happening in the sun's surface that also could have led to the higher temperature seen over the corona compared to that of the sun's surface. So these are the reasons why we are getting a higher temperature over the corona compared to the surface, and it is very highly ionized also. The atmosphere of the sun, the corona is it basically contains ionized particles. So um, because of the interaction of the ionized region and the sun's magnetic field, that could also have led to very high temperature of the over the corona compared to that of the surface. And another one is the solar flares, or this uh, um, tiny explosions that is happening on the sun surface, that also could have led to the very high temperature over the corona. So yeah, those are some of the theories that is actually explaining why the corona is at a higher temperature compared to that of the photosphere. I hope it is clear. And yeah, so that is about the differential rotation. You can always read about this. So I told whatever I like um, what like I found. So you can always read, and then if you find something interesting, you can share also. This is what I found after reading. So if you guys find something else, or if you find that I'm wrong, you can always point it out. That is fine. Oh, fine, Ishika. So yeah, so if you find that I'm wrong at any time, you can always correct me and tell me where I did go wrong, so that I can also learn. Anyway, it will be nice if it is both ways. So yeah. Okay. So I hope whatever I told is clear. If something is not clear, please ask me. I will try to read about it and let you know. Maybe I also maybe won't be able to answer at this point of time, but I'll always try to go back, read, and then I'll let you know. Okay, fine. Then I think we'll move forward. Yeah. So that is all about the sun. I think the things are clear. Now we will see the structure of the sun. As I said earlier, when we discussed or when we talked about the temperature of the sun, we found that at the surface it was at a temperature of 5800 Kelvin, and at the core it was at a temperature of 15.6 into 10 raised to 6 Kelvin. So when we look at the different layers of the sun, at the innermost layer, the center of the sun is basically known as a core. So this is the core. Then outside the core, the second layer, which is known as the radiative zone. And outside the radiative zone, we have what is known as the convective zone. So these three are the interior of the sun. And then the surface of the sun is known as the photosphere. Um, and above the photosphere, we have the sun's atmosphere, which basically has two layers. It is basically chromosphere and corona. These are the two layers of the atmosphere. So we have three interior layers, that is core, radiative zone, convective zone, and we have the surface, which is known as the photosphere. And in the Earth's atmosphere, we have chromosphere and corona. So Tejaswini, who was asking about so as somebody asked earlier, so she was pointing it out that as I said before, the photosphere is at a temperature of 5600 Kelvin, whereas the corona is at a very high temperature of 1 million Kelvin. So that's what Ishika was asking, why this difference is coming between the surface and the atmosphere. Now let us look at how, so these are the different layers in the structure of the sun. Interior layer consists of three layers: core, radiative zone, convective zone. Then we have the surface, which is the photosphere. Then we have sun's atmosphere, which the first layer is chromosphere, and the second layer is corona. Now let us look at how the energy is being transferred from the center of the sun to the surface. So we all know how energy is produced in the sun. Or we are familiar with it. So energy is produced in the sun by the process of nuclear fusion. So basically the hydrogen atoms combine with each other to produce helium atoms. Two electrons plus energy. So hydrogen atoms combine with each other to produce helium, which is associated with an emission of a very large amount of energy. So, because of the nuclear fusion process, this basically happens at the core of the sun. So, during the process, a large amount of energy is emitted, which is basically heating up the core and then leading to the high temperature of around how much it was 5.6 into 10 raised to 6, 15.6 into 10 raised to 6 Kelvin, which basically lead to the very high temperature of 15.6 into 10 raised to 6 Kelvin. That is cool. So due to the nuclear fission reaction through which the hydrogen atoms combine to form helium is associated with the release of very high amount of energy, which is basically heating up the core and then leading to a very high temperature of 15.6 into 10 raised to 6 Kelvin. Now, due to the high temp, so outside the core we have the radiative zone. So due to the high temperature that is present in the core, all the atoms that are present over this region are ionized, highly ionized. So the region is basically in the form of an ionized plasma. So since there are no atoms present in this layer, when the energy is the efficient form of energy transfer from the core to the convective zone is basically through radiation. Because since there are no atoms, no energy will be lost by the absorption uh, of the electrons. No energy will be absorbed by the electrons to get released from there to become free electrons and then get emitted from the atoms or to reach a high energy state. So because of that, because of the high temperature, all the atoms has already been ionized. So the region consists of a large number of ions and electrons. No atoms are present. So all the energy that is being emitted from the core in the form of radiation reaches the convective zone. So initially we have core, which is at a very high temperature. Outside it we have radiative zone, which contains highly ionized particles and electrons. And at core, energy in the form of radiation reaches the convective zone. So while this energy transfer is happening, since the radiative zone consists of ions and electrons, the energy is not, the region is mostly transparent to the, since the radiative zone consists of ions and electrons, radiative zone is transparent to the light or the radiation that is being emitted from the core. It is mostly transparent because of the presence of ion and electrons. Now, when we reach the convective zone, the temperature as we go away from the source will eventually become cooler and cooler. So now, when we reach the convective zone, it is basically consisting of atoms. So mostly atoms are present instead of ions and electrons. The particles are present in the form of atoms. So once atoms are present, then the energy transfer through radiation is difficult because these atoms will absorb the energy that is coming in the form of radiation and and the electrons will use the energy to escape from the outermost shell of the atom. So basically, atoms are present in convective zone. So in this region, the energy is transferred through convection. So convection we know is the process in which energy transfer occurs by the movement of matter. So here the atoms present or the matter present will take up the energy from a point of higher temperature moves up. So here a lot of atoms are present in this zone. So as we know, this region will be at a higher temperature compared to the top of the bottom of the convection zone will be at a higher temperature compared to the top of the convection zone. So what happens is that the atoms present in this layer take up the high temperature from the bottom of the convection zone. It moves upwards. It releases the energy over here because this is such a lower temperature, and then once it releases the energy it becomes cooler and eventually it will come down. Once it absorbs energy at from the bottom of the convective zone, uh, the temperature of the atoms increase and it will be lighter, or the density will decrease. So lower density particles basically rise up. It reaches the lower temperature zone. It basically releases the energy and it again becomes cooler and it will sink down. So like a convection like this is happening in the convective zone. So in this zone, the energy transfer happens in the form of conduction. So now we have reached the bottom of the photosphere. So this is the surface of the sun. So through convection, the energy reaches the surface of the sun, which is basically the photosphere, which is at a temperature of 5,800 Kelvin. Is it? 5,800 Kelvin. So initially we have the core where the energy is produced through nuclear fusion reaction. Hydrogen atoms combine to form helium along associated with the release of a large amount of energy. So from outside the core we have the radiative zone, which basically contains free ions and electrons. So it is basically transparent to the radiation emitted by the core. So through radiation, the energy is transferred from the core to the bottom of the convective zone. So once we reach the convective zone, the temperature is lower. So now no more free ions or electrons are present. The matter exists in the form of atoms. So the atoms are mostly opaque to the radiation. So in this region, the energy is transferred from the bottom of the convective zone to the top of the convective zone through the process of convection, where the atoms absorb the high energy from the bottom of the convective zone. It becomes warm, becomes lighter, it goes up, releases the energy in the top of the convective zone and again comes down. So in the form of convective cells, energy is transferred from the bottom of the convective zone to the top of the convective zone um, by the movement of matter itself, or by the movement of atoms. So now we have uh, the photosphere, which is basically the surface of the sun at a temperature of 5,800 Kelvin. So that's how the energy is transferred from the core of the sun towards the surface of the sun. And above the sun's photosphere, we have the sun's atmosphere, which is the chromosphere and the corona. And as Ishida pointed out, even though the photosphere is at a temperature of 5,800 Kelvin, the corona, or the outer layer of the sun's atmosphere, is at a higher temperature of around 1 million Kelvin, which could be due to because since it is basically ionized. Uh, so due to the interaction with the sun's magnetic field and due to the emission of high energy particles from the sun, the atmosphere is remaining at a higher temperature than the surface of the sun. So the chromosphere is at a temperature of 4,000 Kelvin. So as it is moving away from the surface, its temperature is reducing. Whereas the corona is having a temperature of 1 to 3 Kelvin, uh, 3 million Kelvin. So as we move further from the sun's surface, the temperature due to the complex magnetic field interactions, the corona is having a very high temperature. So then we have chromosphere, the first layer in the sun's atmosphere. It is at a temperature of 8. It ranges from 4000 to 8000 Kelvin. So as we move away from the sun's surface, the temperature increases. It is due to the interaction with the sun's magnetic field. And the corona is at a temperature of 1 to 3 million, 1 to 3 million kilometers. So as we go away from the surface of the sun, the temperature is actually increasing in the sun's atmosphere, which is basically due to the interaction with the complex magnetic field interaction. Because of this, it is actually becoming hotter and hotter as we move away from the sun's surface. So that is about the different layers in the internal structure of the sun and the sun's atmosphere. So I would like to introduce one more term, which is basically known as the solar cycle. So solar cycle is basically an 11-year cycle. Yeah. Solar cycle is solar cycle is basically a 11-year cycle in which the sun's activity increases. It is also known as the sunspot cycle. So sunspots are basically dark surfaces in the photosphere. So these photos temperature lower temperature compared to the surrounding of the sun. That's why it is basically appearing as lower, basically appearing as darker regions in the sun surface. So these are the regions where the magnetic field or magnetic activity is very high. Magnetic activity is very high. Because of this, these regions appear to be at a lower temperature compared to the surrounding. So yeah, so that is sunspots, and the solar cycle is basically sunspot cycle or solar cycle is basically having a cycle of around 11 years where sun's activity increases and decreases. So this is basically happening due to the flip of the magnetic poles of the sun. So a very strong magnetic field is associated with the sun, which has a magnetic north and magnetic south. So basically, the magnetic north and magnetic south of the sun kind of flips every 11 years. So because of this, the activity of the sun is increasing. Yeah. So because of this, the sun's activity increases and decreases. So the magnetic field flips occurs when the sun is at its most active phase or the solar maximum, and this number of solar sunspots peaks around solar maximum and dips around solar minimum. So by counting the sunspots over the sun, basically scientists determine what is the current like at which stage of the cycle is currently the sun now, by comparing the number of sunspots over the surface of the sun. So this basically shows the sunspot numbers. This is basically from European Space Agency. So over the years, they have just plotted the sunspots over the photosphere. So this is from 1700 to 1880, and then lower we have till 2050. What was the number of sunspots over the years? So we can see there is a maximum then it is decreasing, it's reaching a minimum, and then it is again reaching a maximum. I think this cycle basically takes 11 years to complete. So it increases and decreases, then again it increases. So this is happening basically due to the flip in the magnetic field of the sun. North becomes south and south becomes north. And the maximum number of sunspots or the activity of the sun is maximum when this flipping is occurring. So then once the flip occurs, the sun will be at its highest activity, then it keeps on decreasing. Yeah. So that's about solar cycle. So now we will just look at a small equation which can be used to calculate the distance of planets from the sun, which is basically known as the Bot's law. So based on the distance of the planets from the sun, we can determine the based on the position of the planets with respect to sun, we can determine the distance of planets from the sun. So this is basically known as the Bot's. It is given by dn, distance between the sun and the nth planet is given by 0.4 plus 0.32 the whole raised to n minus 2 for n greater than or equal to 2. This is the equation. So n is a number like number at which this placed from the sun. So this is sun. Can someone tell me the order at which planets are spaced with respect to sun? First one is, which is the closest one to the sun? Can someone tell me which planet is the closest to the sun? Mercury. Then Mercury. So first we have Mercury, then we have Venus, Earth, Jupiter, is this right? Did I go wrong here? Mercury, Venus, Earth, Mars, yeah. Mercury, Venus, Earth, Jupiter, Mars, Saturn and Neptune, I guess. Is that right? Okay. So basically Mercury is the first one. Then this is the second one. Then we have Earth, which is the third one, and is equal to 3. After Earth, it's Jupiter, right? So based on this number, we can calculate the distance. So can someone calculate the distance of Sun and Earth with this formula? So n is equal to 3. So this can be used only in case of n greater than or equal to 2, not to Mercury. For other planets we can use. So in case of Earth, n is equal to 3. So can someone calculate the value of dn? It will be distance between the Sun and Earth will be 0.4 plus 0.32 the whole raised to 3 minus 2. which will be 0.4 plus 0.32, which will come sorry, it's n minus 1, not n minus 2. N minus 1. 0.4 plus 0.3. Just a second, I think I made some mistake with the equation. So dn is basically 0.4 plus 0.3 into 2 raised to n minus 1. I'm sorry, I'm extremely sorry. Equation, yeah, this is the equation. 0.4 plus 0.3 into 2 raised to n minus 1. N minus 1. So it will be 3 minus 1, or how much it will be? Yeah. So J is telling 1. Did anyone else get? So the value will be 1. Is that right? Anyone? So the equation gives you the answer in terms of astronomical unit. One astronomical unit is equal to 150 million kilometer. 150. One astronomical unit is 150 million kilometer, which is basically 150 into 10 raised to 9 meter. This is the equation. So you will get a value of 1 astronomical unit. Yeah. Unit will be AU, astronomical unit. 1 astronomical unit is 150 million kilometer, or 150 into 10 raised to 9 meter. So in case of Earth, where n is equal to 3, we are getting a value of 1 astronomical unit. So what will be the value if n is equal to 4? In case of Jupiter, how much it will be? Can someone tell me? In case of, sorry, Mars and then Jupiter, I guess. Yeah, I did. Earth, Mars, Jupiter. Yeah, after Earth it is Mars and then Jupiter. So n is equal to 4 is Mars, n is equal to 4 is Jupiter. Sorry, n is equal to 5 is Jupiter. Yeah. Mars and then Jupiter. So in case of n is equal to 4, in case of Mars, what will be the distance? Yeah. 5.2 angstrom. Is that right? N is equal to 4, it will be 0.4 plus 0.3 into 2 raised to 4 minus 1, 3. That will be 0.4 plus 0.3 into 8. 780 million kilometer, 5.2 AU, 0.4 plus 0.3 into 8. Okay, so yeah, so this is just an equation to calculate the distance of planets from the sun if you know the order at which the planets are situated with respect to sun. So like till now we have gone through what is basically the sun earth system. Sun is the primary source of energy to the earth, and the earth's atmosphere, all the physical, dynamical and chemical process in the earth's atmosphere is driven by the energy released by the sun. And in three different ways, the energy is transferred from the sun to the earth in the form of electromagnetic radiation, in the form of particles through solar wind, and by interaction with the magnetic field. And then we learned what is the diameter of the sun, what is the mass of the sun, the temperature at the surface, core, and at the corona also we learned. I think I'll just add that also. At the corona, just again at a very high temperature due to the interaction with the magnetic field. So 1 to 3 million kilometers. As we are moving away from the surface of the sun, the temperature of the sun's atmosphere is actually increasing. So as we go far away from the surface, the temperature keeps on increasing due to the magnetic field interactions of the sun. So yeah, and then when we look at the composition, the highest constituent is hydrogen, which is approximately 90 to 1%. Then we have helium, 7.8%. Then other naturally occurring elements is composed of around 0.2%. And we talked about the luminosity of the Earth, 4 into 10 raised to 6 watts. And we talked about the rotation of the Earth, which is rotating at different speeds at different latitudes. So it is rotating at a higher speed in the equator and a lower speed at the poles. So it has different length of the days compared to that of the Earth. Then we talked about the structure of the sun. The internal structure of the sun has 3 layers: core, radiative zone, conductive zone. How the energy is transferred within these 3 different zones. Then the surface of the sun is known as a photosphere. The atmosphere has 2 different layers, which is a chromosphere and corona. And we talked about sunspots or solar cycle, which is having a periodicity of 11 years. It is basically determined by the number of sunspots on the photosphere. So sunspots are darker surface that are appearing in the photosphere. Due to the lower temperature compared to the surroundings, it is actually appearing as darker surfaces. These regions have very high magnetic field associated with them. Because of these spots are actually at a lower temperature. Then we learned about Bord's law, which basically gives us the distance of planets from the sun. If we know at what position the planets are located with respect to sun. So we calculated the distance of Earth. So the equation gives you the value in terms of astronomical unit. One astronomical unit is 150 million kilometer or 150 into 10 raised to 9 meter. We calculated for Earth and Mars, right? Okay. So now I hope the things till now are clear. If you have some doubts, you can If you have some doubts, you can ask me or we will move forward. Okay. So now we will talk about the different radiation laws. So these things you will already be familiar. You would have learned during your school, or I think people with his background will know better than me for doing your masters in physics. So I'll just give you a glimpse of the different radiation laws that are important when we are discussing about the Earth's atmosphere, radiation transfer, and all this. We know that. So this basically talks about the spectral distribution of electromagnetic radiation coming out of a black body which is in thermal equilibrium. So as we all know, any body which is at a temperature greater than 0 Kelvin emits radiation at all wavelengths at the electromagnetic spectrum. And depending on the temperature, the wavelength at which the maximum wavelength at which the body emits radiation changes. Also, the amount of radiation the body emits also changes. So, Planck's law, the first one we will be discussing. First one is the Planck's law, which basically gives you the energy emitted by a black body, which is at a temperature of T, that a wavelength lambda. So, any body which is at a temperature of greater than 0 Kelvin will emit radiation. So the energy emitted by this body at a particular wavelength lambda and at a particular temperature T is given by the Planck's law. So it basically gives E of lambda T is equal to 2hc square by lambda raised to 5 into 1 by e raised to hc by lambda kT minus 1, where h is the Planck's constant, which is having a value of 6.626 into 10 raised to minus 34 joule second. C we know is the speed of light, which is 3 into 10 raised to 8 or 2.99 into 10 raised to 8 meter per second. And lambda is the wavelength at which we are calculating the energy emitted by the body. And K is the Boltzmann constant, which is 1.381 into 10 raised to minus 23 joule per Kelvin. And T is the temperature of the body. So how much amount of energy is the body emitting? The particular temperature is given by Planck's law. So these curves represent the energy emitted by a body at different temperature. So the area under the curve basically shows the energy being emitted by the body. At higher temperatures, the energy emitted by the body is also higher. And another thing, when we look here, we will get to know that if we look at the wavelength at which the maximum amount of emission is happening, the peak is actually curving kind of like this. So in case of a body which is at a temperature of 3500 Kelvin, the largest amount of the largest radiation is being emitted by the body at a wavelength of around maybe 800 nanometer, and when it becomes 4000 Kelvin, the maximum wavelength is kind of shifting to this side, towards the left side, which is basically coming around maybe 600. Then again it is becoming 500, 400 like that. So it is kind of, the maximum wavelength is kind of decreasing. As the temperature of the body is increasing, lambda max is decreasing. So one thing that we found from the equation is that higher the temperature of the black body, higher the temperature of the object or the black body, higher the intensity of radiation being emitted. Higher the energy associated with it, higher the intensity of the radiation, and higher the energy being emitted. Second one, higher the temperature, smaller the lambda max. The lambda max is basically the wavelength at which maximum amount of radiation is being emitted by the body. So as the temperature is increasing, we see it is shifting towards the left side. So the lambda max is found to be decreasing. So that is about Planck's law. From this relation, that is higher the temperature, smaller the lambda max, there comes another law, which is basically known as the Wien's displacement law, which basically, so from the equation we understood that lambda max is inversely proportional to the temperature. So Wien's displacement law basically says that only. Wavelength of the peak emission is inversely proportional to the temperature of the black body. So lambda max into, which is basically this, lambda max is inversely proportional to 1 by T. From this we can write lambda max into T is equal to a constant. The constant, let me see, is given by 2898 micrometer into Kelvin. So now, so from this equation, if we know the value of T, we can calculate what is lambda. So, can we try to calculate the temperature of, we can try to calculate the wavelength at which maximum emission occurs from the sun. So, what is the temperature of the sun? Can someone tell me what is the temperature? What is the temperature of the sun?
The photos, the temperature of the photosphere nearly 5,800 Kelvin.
Yeah, exactly. So temperature is 5,800 Kelvin. So can you calculate what will be the wavelength at which maximum emission occurs? What will be lambda max? So lambda max will be C by T. C is 2898 into 10 raised to minus 6 meter Kelvin by 5,800 Kelvin. So what will be the value? Can someone tell me what will be the value?
Nearly 4 into 10 to the power, 4 into 10 to the minus 9 or 10 to the minus 6.
It will be 0.499 or 0.5 micrometer, or we can write 500 nanometer. What is this? This corresponds to which region of the electromagnetic spectrum? 500 nanometer. Yeah. Which region of the electromagnetic spectrum 500 nanometer corresponds to? Can someone tell me? Which region? Like X-rays, microwaves, infrared, like that, which region of the electromagnetic spectrum corresponds to the wavelength of 500 nanometers? Yeah, so it will be in the visible region of the spectrum. So the sun, which is at the temperature of So the sun, which is at a temperature of 5800 Kelvin, emits radiation with its maximum wavelength in the visible region of the spectrum. So when we look at the solar radiation, we will have a peak like this, with this peak corresponding to a wavelength of 500 nanometers. If we plot the solar spectrum, we will get something like this, with the maximum radiation being in the visible range. So that's what this basically tells you. Now, when we are considering the so similarly, we can calculate the energy emitted from the earth also. If we know the temperature of the earth, similarly, we can calculate the maximum amount of the wavelength of the radiation, maximum amount of radiation emitted by the earth also. Now, let's look at another important radiation law, which is basically the Stefan-Boltzmann law. Stefan-Boltzmann law. So Stefan-Boltzmann law basically tells you, the total amount of energy radiated per unit area per unit time by a black body is directly proportional to the fourth power of the temperature of that object. So basically tells you the total amount of radiation, amount of energy radiated per unit area per unit time by a black body is directly proportional to the fourth power of temperature of the object. If T is the temperature of the object and E is the energy emitted by the object per unit area per unit time. So it's just basically E is equal to sigma T raised to 4, where sigma is the Stefan Boltzmann constant. That is Stefan Boltzmann also. So earlier we found the wavelength at which maximum amount of radiation is being emitted by the sun. Now let's see what is the maximum amount of energy that is being emitted from the sun. Again, what is the temperature of the earth? It is around 5800 Kelvin. Can you calculate E? So the value of sigma is 5.67 into 10 raised to minus 8. That's 7 into 10 raised to minus 8 watt per meter square per Kelvin. So it is easy to remember this constant because it is 5, 6, 7 and 8. So it is just 5.67 into 10 raised to minus. Can you tell me the amount of energy that is being emitted from the sun per unit area per unit time? E is given by 5.67 into 10 raised to minus 8 watt meter raised to minus 3 Kelvin raised to minus 4 into 5800 Kelvin given by raised to 4, sorry, 5800 raised to 4 it will be 5.67 into 5800 whole raised to 4. Did anyone get an answer? So this will come around 6.41 into 10 raised to 15 into 10 raised to minus 8, which will be 6.416 into 10 raised to 7 watt meter raised to minus, or watt per meter square. Did anyone get the answer? 6.4 into 10 raised to 7 watt per meter square it will come. This is the energy that is emitted from the sun per unit area per unit time. Is it clear?
Yes, ma'am.
Okay, fine. So we discussed three different radiation laws. First one was the Planck's law, which basically gives you the energy emitted from a black body, which is from an object which is such a temperature T and at a wavelength lambda. Um, that is 2hc square by lambda raised to 5 into 1 by e raised to hc by lambda kt minus 1. So this basically, yeah, you want to say something? Okay,
No, ma'am. No, ma'am. No, ma'am.
okay, thanks. So this basically gives you the spectral distribution of electromagnetic radiation coming out from a black body, which is at thermal equilibrium. And it tells you like higher the temperature of the object, higher the intensity of radiation that is being emitted from the black body. And also higher the temperature, smaller will be the wavelength at which the maximum amount of radiation is being emitted. Then we learned about Wien's displacement law, which basically tells that the wavelength at which maximum amount of radiation is occurring from a black body is inversely proportional to the temperature of the body. This lambda max is directly proportional to 1 by T, or inversely proportional to T. So then from which is basically lambda max into T is equal to a constant. This is Wien's displacement law. So from this we calculated the wavelength at which maximum amount of radiation is being emitted from the sun. So we got the value as 500 nanometer. So now we know that the sun is emitting the maximum amount of radiation in the visible range of the spectrum. Then we talked about Stefan Boltzmann law, which tells you about the total amount of energy radiated per unit area per unit time of a black body is directly proportional to the fourth power of the temperature of the object, which is basically E is equal to sigma T raised to 4. So once we know T, we can calculate the energy being emitted from the body. So again we calculated the amount of energy that is being emitted from the sun per unit area per unit time, just 5800 Kelvin, and we calculated the amount of energy which we got as 6.416 into 10 raised to 7 watt per meter square. So now we know what is the wavelength at which maximum amount of radiation the sun is emitting, and we also know the total amount of energy that is being emitted from the sun. So two things we calculated with the loss that we learned just by knowing the temperature of the sun. So one thing that we understood was lambda max as 500 nanometer. So sun, solar spectrum, peaks in the visible region. second thing we learned was the energy emitted per unit area per unit time by the sun was 6.4 into 10 raised to 7 watt per meter square. So two things we calculated now. Now let us find out the amount of energy that is received at the top of the Earth's atmosphere. We know this much. Now let us see what is the amount of energy reaching the top of the Earth's atmosphere. So per unit area, the sun is emitting an energy of 6.4 into 10 raised to 7 watt per meter square. So what will be the total energy that is being emitted from the sun? If per unit area the sun is emitting an energy of 6.4 into 10 raised to 7 watt per meter square, what will be the total energy that is being emitted by the sun? Can you tell me how calculated total energy emitted by the sun as we know per unit area how much it is emitting? How can we know? Can someone tell me? What is the area of the sun? Area of the sun. Like you can just tell an equation, you don't have to put in numbers. So sun is basically what? What shape it is?
Pi r square.
Yeah, pi r square is area of a circle. So we are talking about sphere. So in case of sphere, the surface area will be, yeah, 4 pi r square. So into 4 pi r square, which will be 6.4 into 10 raised to 7 into 4 pi into r square. What was the radius of the sun? Do anyone remember radius of the sun? What was the value? So the diameter of the sun is having a value of 1.39 into 10 raised to 4 or 1.39 into 10 raised to 6 kilometer. So the radius will be 69500. What is that exactly? Um, Initially we learned about the diameter of the sun. In here I showed you what is the value of the diameter of the sun. Here, if you remember, the diameter of the sun is around 1.3 into 10 raised to 6 kilometer. Now we want to find the radius. So it is basically diameter by 2. So it will be So the value will be 150. Sorry, so it's sorry, sir. You are right. Yeah, it will be 6.9 into 10 raised to 8 square. As as Tejashwini and Ishika was telling, the value will be 6.9 into 10 raised to 8 meter. Yeah. This 69500 or 7 into 10 raised to 5 is in kilometer. When we calculate it to meter, it will be 6.9 into 10 raised to 8 meter. So now when we calculate the total energy that's emitted by the sun, that will come to be 3.9 into 10 raised to 26 watts. This will be the energy emitted by the sun. Total energy emitted by the sun will be 3.9 into 10 raised to 26 watts. Now we want to calculate the amount of energy that is received per unit area at the top of the atmosphere. So we have sun. It is emitting radiation in all directions. We have earth, that is the earth. So from this side, energy is coming towards the earth. So it is just through a disk, if we just assume only through this region. This distance is the distance between the sun and earth. Along, if we assume like through a disk, the energy is coming towards the earth, then we can, this distance is 150 into 10 raised to 6 kilometer. So the energy, amount of energy reaching the earth per unit area at the top of the atmosphere will be S is given by the total energy being emitted by the sun divided by 4 pi r squared, where r is the distance between the sun and the earth. This distance is given by 150 into 10 raised to 6 kilometer. So we are calculating per unit area what is the energy received. So divided by 4 pi r squared. So this will give you 3.9 into 10 raised to 26 divided by 4 into 3.14 into r is distance between the sun and the earth, 150 into 10 raised to 9 whole square. How much will be the value? Can someone tell me? Did anyone got how much it will be? You
What is the new number? 3.9.
3.9. Yeah, that was the total energy that we calculated just.
Yes, ma'am. Yes.
Yeah. 3.9
Got
into
it.
10 raised to 9. Total energy emitted from the sun divided by 4 pi into distance between the sun and the earth, which is 150 million kilometers. So 150 into 10 raised to 9 meter.
And that is one astronomical unit.
Yeah, 1 astronomical.
Um, uh, 1380 watts
Yeah,
means
yeah. There will be 1390 watt per meter square. We are calculating per unit area, so it will be per meter square.
ma'am,
Yeah, 139. Yeah,
dividing by dividing by 4 pi r square, and that is actually basically for the amount of energy, solar energy absorbed by the earth atmosphere per unit solid angle, the solid angle make by earth towards sun, right?
yeah,
Okay, okay, ma'am. Okay, ma'am.
yeah. That's why 4 pi r square. Per unit area we are calculating. That's why we are dividing it by 4 pi, and r is the distance between the sun and the earth.
1380.
Yeah, yeah,
The calculator.
1380. Yeah, no, yeah, not fine. 138. So this is basically the energy received by the earth at the top of the atmosphere. Yeah, at the top of the earth's atmosphere. So this value is basically known as the solar constant. This is known as solar constant, which is basically the amount of energy received by the earth. The amount of solar energy received by the earth at the top of the atmosphere. This value is known as the solar constant. Okay, so this is how it, so initially we got the amount of energy that is being emitted by the sun, which is at a temperature of 5800 Kelvin from the Stephen Boltzmann law. Then we multiplied it with the total area of the sun to get the total amount of energy that is being emitted from the sun in all directions. Then we wanted to find the amount of energy that is reaching the earth's top of the atmosphere of the earth per unit area. So then we divided the total energy emitted by the sun divided by 4 pi r square, where r is the distance between the sun and the earth. Then we got a value of around 1380 watt per meter square, which is basically known as a solar constant. Okay, yeah. So that is the solar constant. Amount of energy, amount of energy received at the top of Earth's atmosphere per unit. Basically, solar energy from the sun, how much energy is reaching the top of the Earth's atmosphere per unit. That is given by the solar constant. This value is this constant is very important, which will come to around 138013, like based on most, as we put most accurate distance between the earth sun, we will get more clear value. So now we got 1380. It ranges between 1374 to 1370 to 1380. So this is the solar constant. This value is very much important in case of atmosphere, in terms of atmosphere. Okay, so that is the amount of energy reaching the top of the atmosphere. Now let's look at some other interesting aspects as well. Two more terms or um, two more concepts I'll just introduce and then we will wind up. So now let's look at how we will estimate the mass of the sun. So basically the earth and sun, this is sun, this is earth, this is two body system. These two bodies are kept together by the force of gravity. The distance is 150 into 10 raised to 9 meter or 1 astronomical unit. These two bodies are kept together by the force of gravitation. The force of gravity or the gravitational force that is present between the bodies are G into sun into mass of Earth by R, which is the distance between the sun and the Earth. And we know that the Earth is revolving around the sun in an elliptical orbit, or this the force required for the Earth to revolve around the sun is basically given by the force of this gravitational force. So the revolution of the Earth around the sun is given by centripetal force, which is mv square by r, where v is the velocity at which the Earth revolves around the sun, and r is again the distance between the sun and the Earth. The force of gravity provides the centripetal force for the Earth to revolve around the sun. So now when we equate these two, this r and this r will go, we will get this. So G ms me by r is equal to, this is again mass of the Earth, mv square. So again this and this will go. So it will be, so now we don't have any mass terms. V square G ms by r will become v square. Now we know that the velocity of the radial velocity can be written as r into omega, just radius into angular velocity. So this will become gms by r equal to omega square r square, which becomes ms is equal to I can go omega square r by g. This is the equation. And then omega is basically the angular velocity is given by 2 pi by t, which is 2 pi by t the whole square into r by g, which will be, and t is the time period which it takes to complete one revolution, which is 365 days. So it will be 2 pi by t the whole square into r by g. Know the value of ms is equal to 2 pi by t the whole square into r by g, which will become, oh sorry, I think I made a mistake somewhere. Okay, the r and r will be r cube, it will become r cube, it won't cancel each other. Here it will be r cube, this won't cancel, r square r, yeah, it will become r cube, omega square r cube by g. Yeah. And t is equal to 365 days, which is equal to 365 into 24 hours in each day, 60 minutes and 1 hour, and 60 seconds and 1 minute. This many seconds it will be. So can you calculate the mass of the Earth, mass of the Sun? 2 pi by t the whole square into r cube by g. Did anyone get an answer? It will come around 2 into 10 raised to 30 kilogram. So this is how we can estimate the mass of the sun. So basically we know the earth and sun are held together through the force of gravity. The equation we know, which is G ms me by r square, and we know that the earth is revolving around the sun in an orbit. So the centripetal force that is required for the earth to revolve around the sun is provided by the force of the gravitational force of attraction, so which both can be equated. Then we derived at an equation where we can estimate the mass of the sun from the time period of revolution of the earth around the sun, the distance between the sun and the earth, and the gravitational constant g. And we found estimated the mass of the sun as 2 into 10 raised to 30 kilogram. Okay, so one more concept that I wanted to introduce was escape velocity. So this also you will be familiar with, but just to uh, revise kind of a revision, we will just discuss this. So escape velocity is basically the velocity required by an object to leave the influence of the gravitational pull of a planet or earth. So the amount of the velocity that an object requires to leave the influence of gravitational pull of a planet is basically given by the escape velocity. So the amount of energy required by the object is given by kinetic energy is equal to half mv square, where v is the escape velocity. So basically the object is held towards the earth by the gravitational pull, which is given by Fg, which is equal to Gm me by m object, water object, by h square, which is the distance between the object and the earth. This is the object. This is the radius of the earth, which is r. Okay. So if the object has to leave the planet, this kinetic energy of the object should equal the force of gravity between the earth and the object. mve square should be equal to Gmm by h square. Now, in order to find the amount of the work done, the work that should be done by the object to okay, sorry, this is in form of force and this is in form of energy. So we should equate these two. We should find the work that the object should do to we should find the object we should find the work done by the object from the force. So work done is given by F dx, right? Force into displacement. So it will be Gmm by h square into dx. If dx is the distance that it should travel. So once you integrate this from x is equal to r, just at the surface, x is equal to infinity, it will become Gm. The total amount of work that the object should do will become Gmm into minus 1 by x. Once you integrate this, you will get this. Now we can equate the both energy and the work done. So it will be half mve square into minus Gmm by x. X, not x, r. Once you integrate from x is equal to r to infinity, you will get minus GMM into minus 1 by R. The negative sign indicates that the energy is being done against the gravitational force. That's why this negative sign is coming. If you want to find the magnitude, we can ignore the negative term, and it will become VE square is equal to G M, and M will go GM by R, or VE is equal to root of GM by R. Now in order root of 2GM by R. Now in order to simplify it a bit more, we know that GMM by R square is equal to mg. That is a force that is acting on a body at the surface of the earth with mass m. And the force that is acting on the body is given by mg. The weight of the body or the force that is acting is mg. And it is basically the acceleration, the gravitational force. Gmn by r square is equal to mg. From this we can write g is equal to gm by r square. So this will become root of 2g into r. This is the escape velocity that is required for the object to escape the gravitational force of attraction of the earth or any other planet. So in case of earth, g will be 9.8 and the radius will be the radius of the earth. So in case of another planet, or even in case of sun, you can just replace g and r. So you will get the velocity, escape velocity corresponding to that particular planet. Yeah. So I think time is over. It's almost 5. I hope the things I discussed was clear. If you have any doubt, please do post on the, I think you have this discussion forums and the NPTEL page. You can post it over there, or you can also ask in the next class, next problem solving session also. We will try to solve issues. I hope things are clear. And thank you. Have a nice day.
Where is the discussion forum?
It is in the NPTEL page actually.
Yes, I have opened that page.
Let me see. I don't have the page open. Can you? Okay, I don't think you'll be able to share, right?
Can I? Can you mail?
Yeah,
Send
I
mail?
will.
Can you give your mail?
Yeah, okay, just a second.
That will be more benefited for us because in the discussion doubt clearing session, in this those session we will meet with you. That is why I'm telling.
Okay, I'm putting my mail in the chat box. If anyone has any doubt, you can. And these lectures are actually recorded, so I will post it in the YouTube also. So you can comment there also. If you have any doubt, you can always comment there also. I will try to uh, check. I have put my mail ID in the